All right, let's pick up with number 22. This topic is work. So I'm going to draw a little free body diagram as I'm talking to myself here. All right, so we have somebody who is pulling a crate with a force of 100 newtons with a rope that makes a 60-degree angle. We have friction that is 10, and he's going to pull the box 10 meters. So what is the net work done? So work is force times distance, but we have to remember that the force has to be the force in the direction of the displacement. And if he's pulling the box 10 meters in this direction, we need the force that is in this direction. But technically, we need the net force in that direction. So let's start by finding what I'm going to call Fx. So that's going to be the x component of this. So that's going to be 100 times cosine of 60, and that turns out to be 50. So I have 50 going this way, but I have 10 friction working against me. So the net force in the x direction is going to be 40. 50 minus 10. And I'm pulling the box 10 meters. So I have 400 joules of work. What is the net work? So all of these units are wrong. These should be joules. We'll fix those right now. All right, the next question is a conservation of energy question. So we have a cart falling from the top of a hill 8 meters high. How fast would the cart be traveling when it reaches the bottom? So at the top of the hill, it has potential energy. And then the insinuation is that all of the potential energy is going to turn into kinetic energy, because it says no loss of energy. And I just need to solve for the velocity. So we can see in this particular situation, the mass would cancel and doesn't matter. And I can put in 9.8 times h equals 1/2 v squared. And then I can solve for v and square root that. And I would get 12.5 meters per second. All right, this question also refers to the situation above, but now we have the cart traveling 10 meters per second when it is at the top, and only 6 meters per second when it reaches the bottom. Calculate the work done by the frictional force. So this implies that we're going to have a loss of energy. So I'm going to kind of redraw the picture. So when it's at the top of the hill, I'm going to call this spot 1. When it's at the top of the hill, it's going to have potential energy. And it left the top of the hill going 10 meters per second. So that means it also had some kinetic energy at the top of the hill. So I could plug in all of these numbers and figure out how much energy it had when it was at the top of the hill. And that's 10 squared. And that turns out to be 642 joules. But as it slides down the hill, it's going to lose some of the joules due to friction. So let's figure out what it has when it's at the bottom. So when it's at the bottom, it has no potential, but it is still traveling at 6. So it has kinetic, 1/2 mv squared. So it's going to be 1/2 times 5, 6 squared. And I number crunch that, and I find out at the bottom of the hill, I only have 90 joules. So if I subtract 642 minus 90, that must be how many joules I lost due to friction. All right, the next question is about power. So we have a student walking up the stairs, a vertical distance of 5 meters in 10 seconds. What is his power output? So power is the work he did over time. The work is his force times distance over time. And so his force is going to be mg times the distance over time. I want to pause for a second. On the exam, many times I did things in variables. So you now can just pick this as the answer, and you don't have to take the time to plug in the numbers and do the number crunching. So don't freak out if something's in variables. It's just designed to save you this extra step. So distance of 5 meters in 10 seconds, and that turns out to be 343 watts. All right, we are now moving into the concept of momentum, impulse and momentum. All right, so we have a 2-kilogram cart traveling at constant velocity subject to an impulse. And we have a graph of the impulse over here. So when you have a force versus time graph, impulse, which is J, is equal to force times time. So that means the area under the curve of this graph is the impulse. So let's find the area. So 2 times 3 is going to be 6. This is going to be 1/2 times the base. That is going to be 2. So the impulse is equal to 8, would be Newton seconds as the unit. What is the change in velocity? Well, impulse is equal to momentum. So therefore we know that the momentum is 8. So I'm going to use the momentum equation is equal to the mass times the change in velocity. So this is 8. The mass is 2. So the change in velocity has to be 4 meters per second. So just remember that an FT graph can give you impulse and momentum. All right, the next thing. You should know some facts about elastic, inelastic, and perfectly inelastic collisions. Let's buzz through them both quickly. Elastic. Momentum is conserved, and kinetic energy is conserved. Inelastic. Momentum is conserved, but kinetic energy is not conserved. And if it's perfectly inelastic, momentum is conserved, kinetic energy is not conserved, and the objects stick together like the picture below. So which of the following is always true about inelastic? Kinetic energy is equal? Nope. The total momentum before is equal to, yep, because momentum is conserved. Do they stick together? Nope, because it's not perfectly or totally inelastic. All right, the next thing is a momentum problem. So we have a picture, 2 objects collide. What is the resulting velocity of the combined? So we're looking for this. So I have mv of the first object plus mv of the second object. This is the collision, and now they are stuck together, and I am solving for this. So plugging in the numbers, we have a 4 and a 15. We have a 2. Here's the key. This velocity is going backwards, so it's got to be negatives. That's a -3. And this mass is the mass of the combined objects, which is 6. And then we can solve for B. And I'm assuming that's going to be 9. So 60 minus, so we have 60 minus 6 divided by 6. That is 9 meters per second. Okay, oscillations. So yes, you need to know your spring facts. Spring facts. So let's just talk about the spring facts before we look at the question here. So the spring facts that you should know. All right, so let's say that we have a wall here. We'll have a spring. We'll have a mass. So this position here is going to be equilibrium. But I'm now going to pull this mass. So this is going to be tighter. And we're going to pull it over here to, this is going to be an end point. So let's talk through our spring facts, what you should know about an endpoint. So since I pulled it over here, I pulled it over in the positive x direction. That means that the restoring force wants to move it back. So the restoring force is going to have a negative value. That's why in the equation F equals kx, there's always that negative sign, that the F and the x always act in opposite directions. So the restoring force is at a max because he wants to go back. And if the restoring force is at a max, it means the acceleration is at a max because he wants to boing back really fast. And it also means that the potential energy is at a max. And then the kinetic energy is 0, and the velocity is 0 because he's temporarily stopped. And now we're going to let him boing back. When he boings back, he will actually pass equilibrium and end up kind of being really crunched over here. But when he passes equilibrium, he now is going to be at a maximum velocity as he's flying past this equilibrium position. And if you have maximum velocity, you're also going to have maximum kinetic energy. And he's now at position x equals 0, which means that he really doesn't want to boing back because he's already back. So the restoring force is 0, which means the acceleration is 0, which also means the potential energy is 0. So these things, these groups, kinetic energy and velocity, are always a pair. And everything else is always a pair. And you can see they just kind of flip-flop positions here. So knowing that, let's answer the question. So, which terms best describe the velocity and acceleration of the mass when it is at maximum displacement? So when we are here, the velocity is 0 and the acceleration is at a maximum. So that should be a pretty simple question if you know your spring facts. All right, the next one is a graphical view of the spring facts. Which graph represents the kinetic energy as it goes between x min and x max? So that means as it goes between here and here, what would the kinetic energy graph look like? Well, in the middle, the kinetic energy is 0, other way around. In the middle, kinetic energy is at a max, and at the endpoints, it's at 0. So kinetic energy is at a max at the equilibrium and 0 at the endpoints. All right, this one's going to take a little bit more thought. So the topic is the sinusoidal nature of simple harmonic motion. And this is looking at things graphically. All right, so what we're supposed to know is that when you look at a graph, that you can extract information from that graph to write the position function. And the position function means x equals the amplitude, and then it's always a sine or a cosine. So in this particular graph, it looks like a sine. So this is sine or cosine. So I'll just write down sine right now. And then w parenthesis t. So that's like the format. So let's extract this information from this graph. So the position function is going to be equal to the amplitude. That is 5, because it goes 5 down, 5 up, so 5. So I picked sine over cosine, but a sine wave technically goes up and then comes down. So this is really like a negative sine wave. So I'll just put that there. So now I need to figure out what W is. So let's talk to ourselves over here. So we can see that the period of this graph, period is the time for a complete oscillation. That's going to be 4 seconds. And frequency is 1 over period, so that's going to be 1/4. And W equals 2 pi f. So that's going to be 2 pi, and then I'm going to put in the frequency. So W is going to turn out to be pi over 2. pi over 2. So I'm now going to write that pi over 2 in for w, pi over 2, and then I have the t. All right, so that's the position function. You can always get the position function by extracting the information from the graph. But now we are asked, what is the velocity function? So the velocity function, in calculus terms, you take the derivative of this function. So we learned that by you just pull the w out. So it's going to become AW. And then that negative sign is going to become a cosine of WT. So let's say it again. The velocity is going to be the amplitude. You pull the W out, the angular velocity, or angular frequency. So you pull that out. It's going to be pi over 2. And you take the derivative of negative sign, which happens to be cosine. And then we still have the pi over 2, and we have the t. So that looks like this one. So on the exam, if needed, I would give you what the derivative of sine and cosine are so that you know. All right. Upon further review, I do not like question 32, so we are not going to go there. I'm just going to cross it off. But the topic of pendulums is something you should review. So this is what you should review. The topic of a pendulum, or the equation for a pendulum, is 2 pi square root of L over G. So T is the period, the time it takes a pendulum to swing back and forth, one time. So you need to know what affects the time it takes a pendulum to go back and forth. The location on Earth and the length of the pendulum. Does the angle that you pull it over matter? No, because it's not in the equation. Does the mass of the pendulum bob matter? No, because it's not in the equation. That's all you need to know. Okay, let's stop this video and we'll finish up the rest in the next one.